Hello and welcome back to Calculus 3. We are starting chapter 16. The first lecture, no coughing, is about double integrals over rectangular regions. And we are looking for volume. So, if I have, in Calc 1, if you remember, if I have a function, f of x, I need to provide some interval a to b, and then I can calculate the area as the integral a to b of f of x dx. Now, the dx was the width of the representative rectangle called delta x, and the height was computed with f. So technically what you have here is the height times the length, which is the area of the rectangle. Now, if you recall at all anything from Calc 1, you would hopefully remember that if you take a representative rectangle and look at it, it would be the f of, I think we use ci times delta x. So f of ci times delta x is going to give you one rectangle, and then you are going to add summation of 1 to n. So this is one rectangle. This is many rectangles, and then you finally hit the limit as n goes to infinity. And this is infinitely many rectangles, and that equals, that was what we called Riemann sum, f of x dx. So when you have a function f of x and you have this one-dimensional input x, when you integrate, you have the height times the width, and you get the area. So now, in Calc 3, for these, now in Calc 3, what you have is you are going to have a two-dimensional input, xy. And that two-dimensional input is going to be bounded, right? And we want that two-dimensional input to be a rectangle for simplicity. So now you don't have any more representative rectangles. Now you have what I call representative French fries. Because what used to be your one-dimensional input AB, now it's two-dimensional input, right? AB by CD. So if you think about this, you're going to have your x, y, z grid, and over here I'm just going to draw some grid. And there's going to be some kind of a surface on top of this grid. So I'm going to pick what I call a representative French fry. The top of this representative French fry will obviously conform to a function. And if you take a look at this representative French fry, it has delta x and delta y on the base. So, and then it has z, which is f of xy, as the height. So this surface over here is z equals f of xy. So now, if you look at this, the volume is going to be double integral of f of xy, and then we'll put dy dx if we're going to go AB, and then CD. Now AB are your limits for integration in x direction, and CD will be the limits of integration in the y direction. So we can calculate the volume by using this integral, and the mechanics of deriving this are exactly the same as the Calc 1, because you have your representative, right, delta x and delta y, those become dx dy. You have the limits between each of them runs, and then you stick the function inside. So is this 3D volume? Of course it's a 3D volume, because you have dx as length, dy as length, and z. So x times y times z is 3D. So it's calculating the volume. So we're all good. Now, to compute double integral, solve the inside first. So first solve the inside. Let's put some of the, let's say you have 0 to 3, 1 to 2 of x squared y dy dx. So there is this inner integral that you solve first, and that's your Calc 1. And that integral will be wrapped in another integral on the outside, which is another Calc 1. So it's like a nested Calc 1 integral. You do one inside, then you do the one on the outside. Later, when we do a triple integral, you just have 3 steps. Solve the inner, then the middle, then the outer. And if I string 16 integrals, you start in the middle, and then you go. We are not going to, because we only deal with double and triple. But even if you string out 16 integrals, you can still do it. You don't need instruction for it. That's what I meant. So I have the outer integral 0 to 3 dx. So that's, you know, something that we copy, and we work on the guts. We are integrating in respect to y. X squared is a constant. So we'll copy x squared, and we have y squared over 2. That needs to be computed from 1 to 2, and you will be plugging that into y because you integrated in respect to y. Then you bring this dx closer. We haven't done anything with the 0 to 3 integral yet, so copy that. Copy x squared. What we get inside is 2 squared over 2 minus 1 squared over 2. Standard f of b minus f of a calculation for definite integrals. And we have 0 to 3 x squared times 2 minus a half is, very good, 3 halves dx. Now you can kick these 3 halves outside, and the integral of this is x cubed over 3, calculated from 0 to 3. 3 and 3 will cancel. You have 1 half, and in parentheses you have 3 cubed minus 0 cubed, which together is 27 over 2. So that's the way to compute double integrals. You compute the inner one, you compute the outer one, and then you just work out the arithmetic. I really like the images that are done in the book. because you get to see what I talked about, the representative French fry and all of that. The same partitioning and what we did in Calc 1. Remember that the finer your partition is, the less error you have, and if you want to get exact area or exact volume, you just have to have infinitely many of them. They're infinitely thin, they're all infinitely stacked, one to the other, and then they actually show the surface. So here is the progression. Over here, you only have 16 French fries in this first picture, and this is approximation. Obviously, the volume would not be great. Each French fry has its own volume. When you add these 16 French fries, you will get. Then you have much tinier French fry, like the string French fry over here. You have 64 in this picture, and you can see that there is less error for the surface because there is less of these sudden drop-offs and things like that. But then we move to 256 French fry version, right, for the same. So these French fries are very, very thin. And then when they become infinitely thin, in the last picture you get the exact, and that's what the Riemann integral is, with the limit when n number of rectangles, or in this case French fry, is sent to infinity. So the integral is given to us, and then all you need to do is to evaluate that integral over the region that it's given to you. Now, the greatest thing about a rectangular region is that you can interchange x and a y. If you don't like dx dy order, you change it into dy dx order. And that's only available when your limits are numbers. We are moving on next class, but these guys are going to be functions, and you can't swap them. You can with pain, but not easily. So what I have here now is, if I want to find, let's go and take a look at some problems. So here is a wonderful example where, let me just try and quickly sketch this one. Okay, so this one needs to go a little bit lower. So what I have here is some kind of a shape. Let's say it's good. So some kind of a shape. And the surface on top is given to me as z equals 24 minus 3x minus 4y. Now observe that the surface on top, guys, has only x, y, and z, which means it's a plane. It's a linear, right? So it's a plane. And if you look at the numbers provided, this number is 3, this number is 2, and the back sits on there is a negative 1 over here for the back side, negative 1. So from the picture, I can see that x is stuck between negative 1 and 3. Y is stuck in between 0 and 2. So just looking at the picture, these are the dimensions that I can use because these are your limits for integration. So now, to find the volume of this object, I will, well, another thing that I like to do before I actually do this is I like to draw the domain because we see exactly what's happening in the domain. X and Y. So X is a -1 and 3. And the Y is 0 to 2. So this is my domain. And you see it's a rectangle from -1 to 3, from 0 to 2. Those are the limits of integration, so it's important. So volume is going to be the double integral of, you have to put in parentheses, 24 minus 3x minus 4y. And then you can put dy dx or dx dy because these are all numbers. Let's do the standard dy dx. And the outer integral corresponds to the limits for that integral. So -1, 3 goes on the outside, and then 0 and 2 goes for the inside one that corresponds to y. So now we copy the outer integral, -1 to 3, and we integrate the inside in respect to y, which gives us 24y minus 3xy minus 2y squared, right? Because it's y is the y squared over 2, and then 2 and 4 cancel. From 0 to 2, and we still have to deal with x's in the next step. So now plug 2 and plug 0 for each of the y's. Well, you don't have to worry about 0. When you plug in 2 for each y, because that's what you integrated, you get 48 minus 6x, and then minus 8 dx. You simplify this, and you are back in Calc 1. So 48 minus 8 is 40, minus 6x dx, and you integrate that to get 40x minus 3x squared when it cancels from -1 to 3. Plug in 3, we have 120, minus plug in 3, you get 27. Plug in -1, that's going to be -40, so plus 40, and the negative gives us another positive. And I have -1 squared is positive 1, so it's just 3. So this is 160 minus 160 minus 27. Well, how about we say just minus 24, because we can combine 27 plus 3.
120. Just brought it down. Oh wait, never mind.
I have a plus 40, right?
Yeah.
You scared me. 136, I hope. Units cubed, whatever. If it was inches, inches cubed. If it's centimeters, centimeters cubed. So whatever it is. Now I know that we only have a minute left, but I still want to talk about this real quick. As you can see, calculating not a problem. Any of that stuff not a problem. The only thing that you guys might run into is the convenient order for integration, because sometimes you really don't want to use a sledgehammer if you don't need to, or to use the sledgehammer. So if you have a region, so integral y cosine xy, and then they put dA because I didn't talk about that. I'll say that dA is equal to dx dy or dy dx. Could be either or. And they also give you that, well, this is over region R, and the region R is given as all of the points x, y, such that x is in between 0 and 1, x is in between 0 and 1, and y is in between 0 and pi over 3. So this is what's given to you. They did not say dy dx, they did not say dx dy. You can pick either one because all of the limits are numbers. So if you swap dx dy into dy dx, you have to swap the limits in front as well on the integral sign. Now, what is going to determine the way we put dx dy or dy dx? Well, you look which one you want to integrate out first. You look at the problem. Which one is easier? Do I integrate out x or I integrate out y? Which one do I want to integrate first in this case? X first. If I integrate y first, like we did in previous two examples, I would have to deal with the, well, what's the product rule called for integration? Integration by parts, yes. Integration by parts. So product rule in integrals is called integration by parts. So if I do dy dx, I have to do integration by parts. But if I do dx dy, I don't have to worry about integration of parts. So y equals cosine xy dx dy. So our integral is y, so 0 and pi over 3 on the outside, and 0 and 1 on the inside.
So as long as you set it up like that, you can just switch it if you want?
You can switch it, yes, and you can only switch it when you have all numbers for limits, because it's a rectangular region. When we go and do the functions next class, tomorrow, you are not going to be switching these easily. So what's my integral over here? Well, my integral over here is going to be integral of cosine is sine. So I copy the constant y, and then derivative of cosine is sine xy divided by y. And I'm going to integrate this 0 to 1, and I still have dy for the integral I haven't done. Maybe over here as a side note, integral of cosine ax dx is, if you don't remember it, sine ax over a plus c, obviously. So cosine ax sine ax, and divided by a. Well, our y has the purpose, has the right like that a. So now you see that y and y cancel, and you just killed the rule by parts, right? When you plug in 1 for x, you get sine y. When you plug in 0, you get sine of 0 dy, and integral of this is negative cosine y from 0 to pi over 3. That's negative cosine pi over 3 plus cosine of 0. Cosine of pi over 3 is, very good, plus 1 equals a half. Can you do this the other way? Sure, but you have to do by parts, right? If you do dy dx order. So we'll reinforce this tomorrow, and we'll learn some new stuff. Also, we'll have the review exam in 2 days because you want to. Bye.